Imagine you're building Uber's internal analytics dashboard. Your operations team wants to see where drivers are concentrated across the city in near real time. But they also want to analyze historical heat maps from yesterday, last week, or last month. How do you design a system that can process millions of real-time location updates, serve low-latency dashboards, and also store historical data for analytics? In this video, we'll design the entire pipeline, from event ingestion to stream processing, data lakes, and OLAP databases. Our system needs to support two very different use cases. First, near real-time heat maps showing driver density in the last 20 minutes. Second, historical dashboards showing hourly aggregated heat maps after 24 hours. We call these the hot path and the cold path, and they need very different architectures. Every Uber driver continuously sends GPS coordinates every few seconds. Each GPS update becomes an event in our system. It contains the driver ID, latitude, longitude, and a timestamp. Simple, but we'll be processing millions per second. We first ingest these events through stateless API servers behind a load balancer. These servers validate the payload and push events into Kafka. Why Kafka? Because it gives us four critical properties: high throughput, durable storage, replayable streams, and it's distributed by design. Now, one important design question. How should we partition our Kafka topic? We partition by driver ID. Why? Because all events for one driver must go to the same partition. This preserves ordering. A driver's GPS updates always arrive in sequence on the consumer side. Partition keys vary depending on system design goals. For Uber tracking, the key is driver ID. For ride matching, you partition by city or region. Payments use user ID or account ID. Notifications use the recipient ID. A chat app partitions by conversation ID. An IoT sensors partition by device ID. The rule is simple. Choose the key that preserves ordering for your business logic. Now here's a clever trick. We don't store raw latitude and longitude directly for heat maps. Instead, we convert coordinates into spatial buckets using Uber's H3 indexing system. This converts the Earth into hexagonal buckets, perfect for heat map visualization. Each GPS coordinate gets mapped to an H3 cell ID, and similar locations land in the same cell. Next comes stream processing. A stream processor like Apache Flink or Spark streaming consumes Kafka events. It continuously updates driver counts per H3 cell. So, at any moment, we know cell A has 25 drivers, cell B has 47 drivers, and so on. For real-time heat maps, we need sliding windows. That means we want a last rolling 20 minutes, not fixed-time buckets. Every minute, the window slides forward. The oldest minute drops off, the newest minute is added. Sliding windows give us a continuously updated view of recent activity. But here's the problem. Storing every individual event for sliding windows is expensive. Production systems use a clever optimization called bucket sliding windows. We divide 20 minutes into 21-minute buckets. Each bucket holds an aggregate count. To get the rolling 20-minute count, we just sum the 20 buckets. This is memory efficient, highly scalable, and gives us approximate but accurate results. The latest aggregated heat map data is stored in Redis for ultra-fast reads. The key is the city plus H3 cell. The value is the driver count. Redis provides sub-millisecond access for dashboard rendering. When the dashboard requests the latest heat map, the backend simply fetches from Redis. Lightning fast response, sub-second latency, ready to render thousands of cells on the map. But Redis cannot store months of history. It's designed for hot data, not cold. So every raw event is also written into a data lake. Kafka branches. One path goes to Flink for real-time. Another path goes to long-term storage. A data lake is cheap, scalable blob storage for raw historical data. Think Amazon S3, HDFS, or Google Cloud Storage. We partition the data by time, year, month, day, and hour. This makes it efficient to query specific time ranges later. Instead of storing raw JSON, we use a columnar format like Parquet. Why Parquet? 3 big wins. Compression. Files are 10 times smaller than JSON. Faster scans. You only read the columns you need. Predicate pushdown. Filters happen at the storage layer, not in your application. Now we run batch EDL jobs to periodically process raw data from the lake. Tools like Apache Spark read the Parquet files. They group by hour, city, and H3 cell. The output? Pre-computed hourly aggregates ready for analytical queries. Aggregated hourly heat maps are loaded into an OLAP analytics database. Think ClickHouse, Apache Pinot, or Druid. These databases are purpose-built for fast analytical queries over massive datasets. Billions of rows scanned in seconds. When a user wants yesterday's heat map at 2 p.m., the query hits the OLAP database, not Redis. The OLAP engine returns aggregated data instantly. Hot data lives in Redis. Cold data lives in OLAP. Each system optimized for its job. Putting it all together, here's the complete architecture. Raw GPS events flow from drivers through API servers into Kafka. Kafka splits into two paths. The hot path, Flink stream processing, aggregating into Redis for live dashboards. The cold path, raw events landing in S3 as Parquet files. Spark batch jobs aggregate them and load results into OLAP. Two pipelines, one unified analytics platform. This architecture pattern powers not just Uber, but almost every modern analytics platform. Food delivery heat maps, fraud detection, IoT monitoring, stock tickers, ad-click analytics. If you understand this pipeline, you understand modern real-time data engineering. Subscribe to System Design Visualized for more deep dives like this. See you in the next one.